mechanics and hydraulics in Unit 2, flow measurement. In the previous chapter, we studied the velocity and acceleration at a point in the fluid flow without taking into consideration the forces causing the flow. This chapter includes the study of forces causing fluid flow. The dynamics of fluid flow is the study of fluid motion with the forces causing flow. The dynamic behavior of the fluid flow is analyzed by the Newton's second law of motion, which states the acceleration with the forces. The fluid is assumed to be incompressible and non-viscous. Equations of motion. According to Newton's second law of motion, the net force acting on a fluid element in the direction of x is equal to mass of the fluid element multiplied by the acceleration in the x direction. Then it is f of x is equal to m into ax. Reynolds equation of motion for flow where f is negligible, the resulting equation of motion are known as Navier-Stokes equation. Hence, Navier-Stokes equation is the equation of motion of a fluid flow in which the pressure force, viscous and gravity force are considered. Euler's equation, Bernoulli's equation. Bernoulli's equation is an ideal incompressible fluid when the flow is steady and continuous. The sum of pressure energy, kinetic energy, and potential energy. Assumptions of Bernoulli's equation is the fluid is ideal, that is, viscosity of fluid is zero. Then the flow is steady flow and incompressible flow, then rotational flow. Bernoulli's equation, it states that in a steady ideal of incompressible fluid, the total energy of any point of the fluid is constant. The total energy consists of the pressure energy, kinetic energy, and potential energy or datum energy. These energies per unit weight of the fluid are pressure energy P by rho into G, kinetic energy V squared divided by 2G, datum energy Z. The mathematically Bernoulli's theorem is written as P by rho into G plus V square divided by 2G plus Z equal to constant. For derivation of Bernoulli's theorem, other classes. Practical applications of Bernoulli's equations. Practical applications of Bernoulli's equations is applied in all problems of incompressible fluid flow where energy considerations are involved. But we should consider its application to the following measuring devices like venturimeter, orifice meter, rotometer, and elbow meter and pitot tube. Venturimeter. A venturimeter is one of the most important practical applications of Bernoulli's theorem. It is an instrument used to measure the rate of discharge in a pipeline and is often fixed permanently at different sections of the pipeline to know the discharges that. A venturimeter has been named after the 18th century Italian engineer Venturi. Venturimeters may be classified as horizontal venturimeter, vertical venturimeter, and inclined venturimeter. A venturimeter is a device. This is the venturimeter. A venturimeter is a device used for measuring the rate of flow of a fluid flowing through a pipe. It consists of three parts. One is a short convergent part, short and divergent part. It is based on the principles of Bernoulli's equations. Next, orifice meter. Orifice meter or orifice plate is a device employed for measuring the discharge of fluid through a pipe. It also works on the same principle of venturimeter. Orifice is which any kind of fluid is flowing. The opening can be of circular, triangular, or rectangular in cross section, and they are named on the basis of shape accordingly. Orifices are mainly used for measuring the rate of fluid flow. It is a device used for measuring the rate of fluid flow through a pipe. It is a cheaper device as compared to venturimeter. It also works on the same principle as that of venturimeter. It consists of a flat circular plate which has a circular short edge hole called orifice, which is kept generally 0.5 times the diameter of the pipe. Through it may vary from 0.4 to 0.8 times the pipe diameter. The differential manometer is connected at the section 1. The differential manometer is connected at section 1, which is a distance about 1.5 to 2 times the pipe diameter upstream from the orifice plate, and at section 2, which is at a distance of about half the diameter of the orifice on the downstream side from the section of plate. A1 is the area of pipe at section 1, and V1 is velocity at section at 1. V1 is the pressure at section at 1. A1, A2, B2, and P2 are corresponding values at section 2. Then now calculate the discharge Q is equal to CD A1, A2 divided by root of A1 square minus A2 square into root 2GH. Its classification of orifices. According to size, it's divided into small orifice and large orifice. Based on the shape, rectangular orifice, circular orifice, and triangular orifice. Nature of discharge, freely discharged and partially submerged discharge. Hydraulic coefficients. Hydraulic coefficients are classified into coefficient of velocity and coefficient of contraction, and finally coefficient of discharge. Coefficient of velocity is defined as velocity divided by C into root 2GH. Then coefficient of contraction CC is area vena contracta divided by area of orifice. And coefficient of discharge CD is equal to actual discharge divided by original theoretical discharge. The relationship between hydraulic coefficients is CD is equal to coefficient of discharge is equal to coefficient of velocity and coefficient of contraction. Next, nozzle meter. Pitot tube. It is a device used for measuring the velocity of flow at any point in a pipe or a channel. It is based on the principle that of the velocity of flow at a point becomes zero. The pressure there is increased due to the conversion of the kinetic energy into pressure energy. In this simplest form, the Pitot tube consists of a glass tube bent at right angles as shown in figure. The lower end, which is bent through 90 degrees and is directed in the upstream direction. The liquid rises up in the tube due to the conversion of kinetic energy into pressure energy. The velocity is determined by measuring the rise of liquid in the tube. Consider 2 points at the same level in such a way that the point is 2 is just at the inlet of the Pitot tube and point 1. Then now we consider the velocity of flow in the Pitot tube for finding the velocity at any point in a pipe by Pitot tube. The following arrangements. Pitot tube along with a vertical piezometer and Pitot tube connected with piezometer. Pitot tube and vertical piezometer tube connected with a differential tube manometer. Orifice. Orifice is a small device through which the fluid passes the thickness of an orifice in the direction of flow. It is very small in comparison to its other dimensions. If a tank containing a liquid has a hole made on the other base through which liquid flows, and such a hole may term as an orifice. Discharge through a small orifice. Basically, discharge is calculated as area into velocity. Orifice is a small opening of any cross section, such as circular, triangular, rectangular, on the side or at the bottom of a tank, through which a fluid is flowing. A mouthpiece is a short length of a pipe, which is 2 or 3 times its diameter in length, fitted in a tank or vessel containing the fluid. Orifices as well as mouthpieces are used for measuring the rate of fluid flow. Then classification of orifice. The orifices are classified on the basis of their size, shape, nature of discharge, and shape of the upstream edge. The following are the important classifications. The orifices are classified as small orifice and large orifice depending upon the orifice and head of the liquid from the center of the orifice. If head of liquid from the center of orifice is more than 5 times the depth of orifice, the orifice is called as small orifice. And if the head of liquid is less than 5 times the depth of orifice, is known as large orifice. The orifice classified as based on shape, circular orifice, triangular orifice, and rectangular orifice, square orifice, depending upon their cross-sectional areas. Then the orifices are classified as based on the shape, short-pitched orifice, bell-mouthed orifice, depending upon the shape of the edge of the orifices. The orifices is classified as free discharging orifices, drawn or submerged orifices, partially submerged orifices, depending upon the nature of discharge. The submerged orifices are further classified into fully submerged and partially submerged orifices. Flow through orifice. Consider a tank with a circular orifice is one of the sides head of the liquid above the center of orifice. The liquid flowing through a orifice at a jet of liquid whose area of the cross section is less than that the orifice. The area of jet fluid goes on decreasing at a section. The area is minimum. This section approximately at a distance of half of the diameter. At this section, the stream lines are straight and parallel to each other and perpendicular to the plane of the orifice. This section is called as vena contracta. Next, mouthpiece. An orifice with prolonged sides is called as an mouthpiece or tube. In other words, a mouthpiece is attachment in the form of a small tube fixed to an orifice. When the tube is fixed externally, it is known as external mouthpiece. If it is fixed internally, it is called as internal mouthpiece. Depending on the shape, mouthpiece can be cylindrical, convergent from divergent, or of any other form. The mouthpieces are classified as external, internal, depending upon their position. The mouthpieces are classified cylindrical and convergent mouthpieces, convergent from divergent mouthpieces, depending upon their shapes. The mouthpieces are classified as mouthpieces running full, mouthpieces running free, depending upon the nature of discharge at the outlet of the mouthpiece. This classification is only for internal mouthpieces, which are known as Bordas mouthpieces. A mouthpiece is said to be running free if the jet of liquid after contraction does not touch the sides of the mouthpiece. But if the jet after contraction expands and fills the whole mouthpieces, is known as running full. A mouthpiece is a short length of a pipe which is 2 or 3 times its diameter in length. If this pipe is fitted extremely to the orifice, the mouthpiece is called an external orifices increases. In problems, we see this as for orifice and mentimeters problems.